I will go over this question on mathematical induction. That is a topic that appears in the Pure Core module of the Further Maths course. I will assume that you are already familiar with mathematical induction and the ideas behind it. So I will not introduce the topic here. I will just answer the question for you, which says, prove by induction that for every integer n is greater than or equal to 1, 11 to the power of n minus 3 to the power of n is divisible by 8. You're quite welcome to pause the video, prove it yourself, and then compare your solution with the model answer. Okay, so I will continue. The first thing you do with questions like this is you restate the question as a proposition. So the proposition is that 11 to the power of n minus 3 to the power of n is divisible by 8 for all integers n is greater than or equal to 1. I will follow the format of the Pure Core textbook that you will be familiar with. It is important with these proofs that you structure your solution always in the same way. And if you do that, every step follows naturally from the one before. And in a sense, the question answers itself. So after writing down the proposition, we go to what we call the base case. N equals 1 is the smallest allowable integer here. That is our base case. And when n is equal to 1, the expression becomes 11 to the power of 1 minus 3 to the power of 1, giving us 8, which is divisible by 8. So we've shown that for the base case, the proposition is true. The next step is to assume that the proposition is true for some n equals k. So having proven the base case, we now assume that it's true for some value of n that we call k. And then in this case, 11 to the power of k minus 3 to the power of k must equal some multiple of 8. So we're assuming that it's true and that it produces a multiple of 8. So this is an integer divisible by 8. Having done that, we go to the next integer along. So when n equals k plus 1, the next integer after k, we are working towards (11 to the power of k plus 1 minus 3 to the power of k plus 1 must also be a multiple of 8. 8 times something else, some other integer, not a anymore. Okay? Right, what does this mean? This means that we're assuming that the proposition is true for n equals k, and if we can go to n equals k plus 1 and show that this expression also gives a multiple of 8, then essentially we have proven the proposition. And so we start left-hand side. The left-hand side is 11 to the k plus 1 minus 3 to the power of k plus 1. So we are aiming to show that this produces a multiple of 8. And we're going to write 11 to the power of k plus 1 as 11 times 11 to the power of k, using the simple rules of indices. Minus 3 to the power of k plus 1. We're about to make a substitution here for 11 to the power of k. And how do we do this? If we go back to this line here, we can rearrange this to make 11 to the power of k the subject. So we bring the minus 3 to the power of k term to the right hand side. So I'll just write it here. 11 to the power of k equals 8a plus 3 to the power of k. And now here we write 11 times, and then instead of writing 11 to the power of k, we write 8a plus 3 to the power of k. And don't forget the minus 3 to the power of k plus 1. Right, multiplying this out, we get 11 times 8a plus 11 times 3 to the power of k minus 3 to the power of k plus 1. Equals 11 times 8a plus 11 times 3 to the power of k. And now we can write 3 to the power of k plus 1 as 3 times 3 to the power of k, which is 11 times 8a plus. Okay, we have two terms here with 3 to the power of k common to both. So we can take it out. We can factorize by taking out. So we leave inside the brackets 11 minus 3. 11 minus 3, and then you put on the outside times 3 to the power of k. Equals 11 times 8a plus, well, 11 minus 3 is 8. 8 times 3 to the power of k. And now we can take out the 8 that is common to both. So it's 8, open brackets, 11a plus 3 to the power of k, which in fact equals 8b, for b equals 11a plus 3 to the power of k, which in fact gives us our right hand side from here. So we've shown now that for the case n equals k plus 1, we do indeed produce a multiple of 8 on the right hand side. And of course this is here, which is, pardon me, divisible by 8, what we wanted. Okay, so hence the proposition is true for n equals k plus 1. So we've done it. but it is important that at the very end you wind up your proof with a conclusion. And marks will be awarded for this, so make sure that you do it. So to finish off, you write the proposition is true for n equals 1, our base case, and if it is true for n equals k, it is also true for n equals k plus 1. Hence, the proposition is true for all n is greater than or equal to 1, all integers that is, by the principle of mathematical induction. And this winds up the proof. This is enough. But I want to show what might have happened if we'd approached this step here differently. So if I now go back to the beginning, I mean, you can stop the video now and leave it. I mean, the proof is complete. I just want to show what would have happened had we taken a slightly different approach with the n equals k plus 1 case. And if I'd written here instead 11 to the power of k plus 1 minus 3 times 3 to the power of k. Just now I wrote out the left hand side as 11 times 11 to the power of k minus 3 to the power of k plus 1. But now instead I'm splitting the 3 to the k plus 1 term instead of the 11 to the k plus 1 term. So what would have happened had you done it this way? I'm not going to do the full proof. I just want to show where it leads. And this is going to be 11 to the power of k plus 1 minus 3 times, and we will make a substitution for 3 to the power of k. And if we go back to the n equals k case here and rearrange that, we can write 3 to the power of k equals 11 to the power of k minus 8a. Just rearranging that, bringing 3 to the k to the right hand side and the 8a to the left hand side. And so here, instead of writing 3 to the power of k, we can write in brackets 11 to the power of k minus 8a. Which is equal to 11 to the k plus 1 minus, multiplying the brackets out, 3 times 11 to the power of k plus 3 times 8a minus minus, careful. We can now split 11 to the k plus 1 as 11 times 11 to the power of k, and then minus 3 times 11 to the power of k plus 3 times 8a. And here we have 11 to the power of k common to both, so we can factorize this as in brackets 11 minus 3 times 11 to the power of k plus 3 times 8a. The bracket, of course, 11 minus 3 gives you 8, and we're left with 8 times 11k plus 3 times 8a. And again, we get an 8 that is common to both, so we can take it out. And then write in brackets 11 to the power of k plus 3a, which is divisible by 8. So you can see here that had we taken a slightly different approach from the previous one, we would have still nevertheless ended up with a multiple of 8 on the right hand side. So the proof would have worked one way or the other. I hope this helps.